the probability distribution of all the combinations of values. You have marginals, you have conditional distributions. Okay? And the way we describe statistical association is always done in terms of these three objects. So, how do we do it? Well, for example, statistical independence. Is written like by saying that probability, the joint probability distribution P of S1 and S2 is just the product of the marginals. So notice that this is a massive reduction in complexity, because if I can say that, then remember that to quantify the empirically this guy, I need in principle B squared data points. However, the marginals I can describe only with B data points. If my quantization, so the number of levels is, say, 10, so that means here I need, if I can say the variables are independent, I need 10 data points, here I need 100 data points. That's a massive reduction in complexity. Why is this the good definition? So, in order to understand that, you have to understand conditional probability, right? So conditional probability tells you that the probability distribution for S2 is a function of S1. Now, in the case in which S1 and S2 are independent, what I want is that this function is a trivial function that in fact doesn't change when I change S1. Because that's the statistical way to say S2 doesn't care about S1. Right? So it doesn't care about S1. So then let's write who this conditional distribution is. And you can see it from here. So what is this distribution? Essentially, I'm taking this bell and I'm cutting a slice, a section through it. Right? So when it's like when you slice a brain, you make coronal sections. So here we're making coronal sections of a probability distribution. And so that means that essentially what I have is the joint probability distribution calculated at a particular S1 level. Let's say S1 is equal to S1 hat. And this is S1 hat. So I'm just slicing through this, keeping S1 constant and following S2. And that's this thing, right? So am I done? No. Why? you remember that a probability distribution, to be a good probability distribution, has to adapt to 1. However, so the total area of this distribution here, of this section, will depend on where I cut the section. For example, if I cut the section here, I get a tiny area. And here I get a bigger area. If I cut through here, I get an even bigger area. That means to get something that I can add up to 1, I need to divide by something, which is this total area. And the total area is just the marginal probability of S1, because that's the total probability of finding S1 here regardless of S2. Okay, so now you can understand statistical independence. Why? In the case of statistical independence, who is this guy? So P of S2 given S1. Well, let's use this formula. The joint probability distribution is now the product of the marginals. And at the denominator, I have the marginal for S1 again. And this guy simplify, and I'm left with PS2. And that means what I was telling you before is the case. That when the two variables are independent in this sense, S2 doesn't care about S1, which means that its conditional probability doesn't depend on S1. Okay? So this is a formal definition, and this helps you understanding why that definition makes sense. The fact that we say you can factorize this joint distribution, which means factorizing means writing a function as a product of simpler functions. The fact that you can factorize this distribution in this way tells you that you have good concept of statistical independence. Okay.
Okay, one quick question. So the bottom formula, so the right hand side, the numerator, would you explain that?
This.
The top one.
This.
Right.
Yeah. So this is, all I'm saying is that, so I have a 2D, imagine you have here
that's the coronal slice?
A 3D, yeah.
Okay.
And then I'm just following this, cutting a section and following the section. So while keeping S1 constant and changing S2. Mm-hmm. Right? So that is the idea. Right? So that's it's a probability distribution slice. But there is this extra term which is a normalization which I need, because otherwise I would get things that don't add up to 1. And you can demonstrate that this is the correct normalization.
And that then comes into the Bayesian formula as well, right?
Yes. Yeah. Actually, maybe what I'm going to do is I think I'm going to skip the information theory stuff that I treated last time, and maybe we'll treat again, but from here, I want to go again I want to go to Bayesian formalism. So Bayesian formalism is based essentially on conditional probability distributions, and it's based on a way to interpret these probability distributions. So I told you so that yes, a probability is some sort of abstract formalization of the concept of the histogram. So I have a histogram like that, these are data, and I'm going to say, yeah, this is representative of the probability distribution. That will go more or less like this, because if I repeat the experiment n times, I will see this value a number of times, that is p multiplied by n. This is one interpretation of the meaning of probability. And this is called the frequentist interpretation. So Reverend Bayes in the 18th century came up with another idea. And the idea is that probability is not about representing the result of an empirical experiment. Probability is about expectation. Right? So it is, regardless of whether I've ever performed this experiment, it is what I expect the result of this information to be. Okay, and that you can, in a very practical way, you can understand in the concept of gambling, right? So suppose that you wanna gamble on the outcome of a coin toss, right? So that you know that if the coin is fair, you have you're gonna have the same probability of getting heads and tails, which means that if I offer you to bet at even odds on the fact that heads come up, so I'm the bookmaker, and I'm offering you even odds for a bet that next coin toss will be heads, you may take it, right? If I offer you 2-to-1 odds, you would be very willing to take it. If I offer you 1-to-2 odds, you walk away, right? So, and how do I measure whether the coin is fair? Well, I could say I throw it 100 times. If I get that on average, I get around 50 heads and 50 tails, I can say that's fair. Now suppose that I want to bet on a football game. In a football game, I don't know the exact odds between Ajax and PSV or something, right? So I have an expectation about the likelihood that Ajax or PSV will win. And my expectation will be different from that. So the odds that I am willing to take, so the sweet spot, so the lowest odds that I'm willing to take, actually represent my representation of my expectation for the probability that one of the two teams will win. Okay? So of course that particular game will always be an n of 1, because that particular game you can only play once. Okay? So you cannot have a frequentist interpretation because there's not going to be any empirical histogram. There's only one data point. Okay? So that's the first thing. So Bayesian probability is about expectation. So the next step is, and then I can say, so P of x, let's say x is a variable that says x is 1 if tip A wins, and it's 0 if team B. And now I have a P of x, which represents my understanding of the game, of everything I know about the two teams, weather conditions, anything. Now suppose that I have an extra variable, and that variable can call it y. And y is 1 if player G, who is the superstar of team A, plays, and it's 0 if player G doesn't play. Yeah. Now you see by yourself that it makes sense to talk about a P of x given y. Because based on whether player G plays or doesn't play, I'm going to have a different expectation for the outcome of the game. Okay, so in Bayesian terms, we call this the prior probability. So this is the probability about the outcome of the game before I know any additional information. And this is the posterior probability. This is the probability after I heard whether player G plays or not. We're talking about football. Okay.
Can I say one thing? So
Yeah.
I have to run animal experiments.
Yeah, but we're going to
Okay.
finish. Yeah.
So should I wait or?
No,
Yeah.
let's finish here.
Yeah.
So we will continue. But let's try to keep in mind these 3 things or 4 things. Frequentist probability is about representing the outcome of repeated experiments. Bayesian probability is about the expectation about an outcome, not requiring necessarily repetition. And data, new data changes your Bayesian probability, so your expectation about an outcome, and it changes in a way that, so you go from a prior probability to a posterior probability. Prior is before I know the new data, posterior is after I know the new data. And the Bayes rule gives you a way to actually go from one to the other of these objects, and allows you to do things like prediction, decoding, and things that we'll discuss next time. For example, also this video tracking that I showed you before, you could express as a Bayesian problem. And actually, if we do a journal club next time on this, there's about, in the supplementary material, there is a kilo of Bayesian statistics. All right.
Happy birthday, Lisa.
Oh, by the way, if anybody's interested, so I'm just throwing it there, and actually it conflicts with all the journal clubs.